Welcome back to Mathematics Lifeline. In today's video, I'd like to go over Gabriel's horn and why it's such an interesting result in mathematics. Now, this is something that you'll see in probably early in your Calculus 2 class. You might not even get this particular example. However, we're using concepts in Calculus 2 to show the interesting result of Gabriel's horn. So I'm not going to spoil that just yet. I'll let you wait till the end of the video to see how interesting this is. But essentially, what Gabriel's horn is we take the graph y equals 1 over x, and we revolve it all the way around the x-axis. We see this is the x-axis right here, this is the y-axis. We're going to revolve it all the way around. And this is what's known as a solid of revolution. So now you can see in this rough picture that I've made that it goes all the way around this point x equals 1. Now that's what's important. That's what gives us such an interesting result, is that it revolves around x equals 1. So we're really not even worried about this part of the function. We're just worried about this horn shape that it makes. And you can kind of see it comes into a point, kind of like a cone. So what we want to do is figure out what the volume and the surface area of this shape is. So we see that this goes off to infinity. So you might think that the volume is infinite, and as well as the surface area. But we'll see when we calculate surface area and volume that it's not exactly what we think. So let's go ahead and do this. So first let's start with the volume. So the volume of a solid of revolution, we use this formula, the integral from a to b of pi times f of x squared dx. This is the formula that we use to find the volume of a solid of revolution. Now, of course, we know that the function here is 1 over x. We have that right here. And a to b is going to be 1 to infinity in this case. So the volume is going to be equal to the integral from 1 to infinity of pi multiplied by 1 over x squared dx. Now, we can pull this pi out front. So we have a pi times the integral from 1 to infinity of 1 over x squared dx. Now, instead of leaving this as 1 over x squared, we're going to use the exponent power rule to see that we can actually change this into x to the negative second power. This is x to the minus 2. Now, the final thing we need to look at before we evaluate this integral is that we have an integral from 1 to infinity, and this is an improper integral. So we need to set up a limit. So we're going to have the limit, we'll say as b goes to infinity, of pi times the integral from 1 to b. You see we're just changing infinity with b here, of x to the negative 2 dx. So now we can evaluate the integral. So we know that the integral of x to the negative 2, we can use the power rule. So don't forget we have this pi and we also have the limit. So limit as b goes to infinity of pi multiplied by, this one is going to be x to the negative first over negative 1. So x to the negative first over negative 1. This is evaluated from 1 to b. So now this actually will turn into negative 1 over x by bringing this down and making it negative. So this is negative 1 over x. And now we're just going to plug in using the definition of the integral of a definite integral. We know this is actually now the limit as b goes to infinity of pi multiplied by, we're just going to plug in b. So we have negative 1 over b minus negative 1 over 1. Now we plug in the 1 and we subtract. So since we have a limit as b goes to infinity, if we plug in infinity here, we know that the bottom is going to get increasingly big. So this entire part right here will turn to 0. We have minus negative 1 over 1. Well, negative 1 over 1 is just going to be negative 1. Minus 0 minus negative 1 is equal to 1. This is the same as pi multiplied by 1, which of course is equal to pi. Now this is the volume of this shape. How is it a finite volume if this gets increasingly small but it never actually touches this x-axis? Well, that's what's so interesting about Gabriel's horn, is that we have a finite volume here. We get a finite value and it's pi, which is what makes it even cooler. Now, of course, this is an interesting result, but now we need to do the surface area. And we think, well, if this is a finite value, if the volume is finite, then the surface area probably is too. But you'll see that it's not exactly what we think, and this is what makes it so cool to work with. So let's go ahead and do the surface area right now. All right, so now we want to evaluate the surface area of Gabriel's horn. So this is the formula that we use, the integral from a to b of 2 pi times the function multiplied by the square root of 1 plus the derivative of the function squared. Now this is a much more complicated formula that we use for surface area, but we see that we can evaluate it in kind of the same way, and we'll work through that in this part of the video. So first, let's find the derivative of our original function, because we need that for this one. So if f of x is equal to 1 over x, this is also x to the negative first. So f prime of x, we're going to use the power rule. We get negative x to the negative 2, which is negative 1 over x squared. So this is our derivative that we'll plug in right here. So let's go ahead and evaluate this integral. So we know that a and b are going to be 1 and infinity, just like in the volume formula. So we're going to need a limit. So we're going to have the limit as b goes to infinity, the integral from 1 to b of 2 pi times the function, which is going to be 1 over x, and that's multiplied by the square root of 1 plus the derivative squared. Well, this is negative 1 over x squared. All of that is squared dx. And of course, this is equal to the surface area. That's the surface area of this entire shape. So when we evaluate this, that's what we're going to get. Go ahead and erase this to give us some room. So one thing that we do need to notice right here is this term. It looks really complicated, and we don't want to have to integrate something like that. So instead of actually integrating like this, we're going to notice that this term is always going to be positive. It's always going to be greater than 1. So, because when we square this whole thing becomes positive, and we have 1 plus, and the square root of anything greater than 1 is going to be greater than 1. So we know that this term is always going to be greater than 1. Now, because we know that, we can actually get rid of this whole term and just say that our new integral is less than the surface area of A, because we're taking away a positive term. So we know that it's always going to be less than the surface area. So we can rewrite this as the limit as b goes to infinity of the integral from 1 to b of 2 pi times 1 over x dx. Just completely getting rid of that term, that way we don't have to deal with it. Now, we know that this term is going to be less than the surface area of Gabriel's horn. Now, we can evaluate this so that we can pull out this 2 pi because it's a constant. So we have the limit as b goes to infinity of 2 pi times the integral from 1 to b of 1 over x dx. And of course, we know the integral of 1 over x dx. So this is going to be equal to the limit b goes to infinity of, this is 2 pi multiplied by the natural log of the absolute value of x evaluated from 1 to b. Now, important to note that the natural log of 1 is always going to be 0. So we really just have the limit as b goes to infinity of 2 pi multiplied by the natural log of the absolute value of b minus 0, because that second term, when we plug in 1, is always going to be 0. Now we'll just plug in infinity here. So we really have 2 pi multiplied by infinity, and we know this is going to give us infinity. So that tells us that our integral here is evaluated to infinity. But we also know that this entire integral right here that we evaluated to be infinity is less than the surface area. So that tells us that the surface area is greater than infinity. So that means that the surface area is also equal to infinity. Now this is what's so interesting, is because we can, let's think about this in terms of paint. We could fill this thing, this entire horn, with a finite amount of paint, and that finite amount of paint is exactly equal to pi. But if we were to paint the surface of this shape, we would never stop painting. And that's what's so interesting about Gabriel's horn. Such an interesting concept that we can have a finite volume while also having an infinite surface area. But yeah, that's about it for this video. I hope that you enjoyed this. I know that when I first learned about this, I was super intrigued, and I just hope that this gives you a little bit more insight into Gabriel's horn and the sort of paradox that it is. It's very interesting. You learn this in Calc 2. These are solids of revolution is what this is called. The more general form, this is called a solid of revolution. But yeah, that's about all I got for you all this video. Please let me know if you enjoyed it. Let me know if there's anything else you'd like to see in the future. But if not, then I will see you in whatever the next video I make is. Thank you all for watching and have a good one.